Unit, shall we?
Unit 2.
Yay!
I hope you're stressing the E's part.
I know. All right, so one of the first things you're going to see here in a minute is the classification of matter. Not so surprising, right? But if I were, let's go ahead and just doodle an atom up here. Okay, what three pieces make up an atom? You've heard this before. I'll write them down. Name one. Protons, I like them. Protons, little plus. Neutrons, 0. And what was the other one? Electrons. Exactly. And so these things, electrons be what symbol, you think? Maybe a minus sign. Very good. I like it. She's so funny. Okay, so that's cool. And so an atom, it's got those three pieces, but you know physicists actually take those pieces and break them down even further, drat them. And I know, and one way they can take a proton and make it smaller is use a what they call a particle collider, a hadron particle collider, whatever. Basically, they take two protons and they make them go really fast around a track that's like 17 miles, in diameter, make them go really fast. And then they put them on a trajectory and they're going opposite directions. Then I can't do that by, and then they ram them into each other and they make little pieces. So anyway, an atom is very tiny.
How small would
I know. Very, very small. It's inconceivable how small like a neutron or a proton would be. But one of the things is these are munitions. Oh, little BBs, right? So, and I'll have this on a slide, but just to get the sense of what how small an atom is. Okay, of those, 2 of those particles, list you guys told me, are in the center of an atom. Which 2?
The neutron.
Very good, protons and the neutrons. So when we get to drawing an atom here this week, we're going to go, this is the center of an atom, and I'm going to put a proton in there. Plus, and I'm going to put a neutron. Neutrons are like Switzerland, they're neutral. Okay, so that is, starts with letter N, what do we call that center of a nucleus? Very good. What we've just described is the nucleus. Okay, and the electrons are, we'll be talking more about this cloud, but the electrons are in a cloud outside the nucleus. That's where the electrons are. And so kind of drawn to scale, if you can find my BB down there, okay, that would be the protons and the neutrons. The nearest electron in general would be about 5 stories. So if a story is maybe 10 feet tall, about 50 feet away, if that was to scale. The nearest electron. That is so cool. I love it. Okay. So that's an atom. That is an atom. I just think that's so neat. Okay. So this is how you classify matter. Actually, you guys on your Unit 1 exam answered some questions. Are you finding it, Robert?
Working on it.
Okay.
Unit 1, Part 9, or?
Unit 2, Part 1. So you guys answered some questions on your exam, first unit exam about this. And remember how this goes. Clear down here at the bottom. You know, if a substance is pure, then it's either an element or a compound. We've been talking about that. Otherwise, it's a mixture, and it's well-mixed, homogeneous, or it's chunky, it's heterogeneous. But if it's a pure substance, element, or compound, you can go back and forth between, you can take a compound and break it down into its elements by a chemical reaction, CHM122. Okay? You can take an element and build it up into a compound by another chemical reaction. Okay. But the point that I think the previous slide says is if that you have just an atom, if you have an atom, that's one particular element, a hydrogen atom or a helium atom or a magnesium atom, you can't break that down any further with a chemical reaction even. Another type of reaction called a nuclear reaction, right? Nuclear reactors. Nuclear reaction, you can break down an atom even more. Okay, so So atoms. So periodic table. Sometimes students will say, do I need to memorize that? No. Would it be nice? It wouldn't even help you, but it's pretty. Okay, I'm going to give you a few to memorize, the names and the symbols. Speaking of, let's go around the room. I know it's Monday, but for 5 extra credit points, so how many do you have? 1, 2, 3, 4, 5. Well, we'll have to come up with something else. There's only 6 there, and we have 4, 6, 8. Okay, that's okay. We'll get you. So tell me what. We'll start up here with Nina. Carbon. What's the symbol for carbon?
Capital C.
It is a capital C. Ding, 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 ding. You guys, everybody's kind of looking which one I'm going to get. And you can look in your notes and all that. These would be a handful of ones that you may or may not kind of know off the top of your head. Like this, and I like what Nina said. She said capital C, and she's right. And so what like this slide says is like the next one, hint, hint, if there's 2 letters that make up the symbol, the first one's capital, the second one's lowercase. So what's the symbol for copper? Capital C, lowercase u. Ding, 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 ding. Allie? Capital C, lowercase o. Cobalt's a good one to pick on because what's capital C, capital O? Carbon monoxide. Yes, exactly. That's not the same thing as the element cobalt. Okay, Robert.
Capital N, lowercase.
Capital N, lowercase a. Ding, 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 ding. Very good. Iron. Emily?
F-E, seriously?
F-E. Yeah. Capital F, lowercase e.
But I mean, really?
You win. Special blank cereal. What is the symbol for potassium? K, it is. Ding, ding, ding. And if we don't get you, you guys got 5 points anyway. So we'll just see. Is that not fair? Okay, go ahead.
Just wondering, how is iron Fe? Like,
Those-
I understand that it just is.
It's Latin, I want to say.
Okay.
Yeah.
I'm like, I don't understand how
Yeah.
it randomly is Fe.
Right. In fact, that brings me to this. It's hard to kind of see these, but there's periodic tables that tell you different information. And what this does is it tells you the year that these things were found. Which
No kidding. That's awesome.
Yeah, I know. I think so too. Like I said, the older I get, I'm getting an appreciation for history. So let's find FE on there. See what year it was found.
It doesn't have a year. Says ancient.
Ancient. Dot. Okay. That's interesting. And the things in parentheses look like they are they're the nationalities. This is kind of dated. Can anybody tell me why this looks like it's dated? Look at the last element. Like it kind of peters out at 106.
Of question mark?
Yeah. This periodic table we have in the room here goes up to 114. Okay, which of the 3 particles did you tell me which one has a plus charge? Protons. Those numbers that you see here, the numbers for the boxes are those numbers like 114. Those numbers are always the numbers of proteins. Protons in the center of an atom of that type of element. Isn't that cool or what? So start to be we'll talk more about that. And so it increases by numbers of protons. And it goes across, dun, 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 and then it does another row. Dun, 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 dun. Okay? So just kind of getting yourself oriented to the periodic table. So, Cameron, the symbol for copper is?
That would be C, capital C, lowercase u.
Very good. All right. So find one more. These are just kind of some close-up pictures of copper. Let's see if this will animate for us. It should, but it is Monday. Lest you not pay attention, these won't be necessarily, they could be on the test. I'll let you know. These would be fair game. This almost gets back to the top one almost gets back to an astronomy question. One of the things we learn in astronomy is we definitely look beyond the Earth. We look beyond our solar system. We look beyond our galaxy. And if you look at the universe as a whole, the most abundant element is hydrogen. It is weird. It's cool. I mean, because if you think of hydrogen, well, hydrogen's is used in H2O, right? Water, but
It's everywhere.
it's everywhere. And then another thing, this is actually meteorology down here. I think they had this on their quiz or their exam last week, was if you're walking around the room breathing in air, most of it's nitrogen. Yeah. Though we're going to look at a little pie chart to kind of emphasize this. If you look at the Earth's crust, most of it is oxygen.
Weird.
That is weird. What's that?
You're thinking liquid.
Isn't it like if you have too much of it, it can be poison?
You can OD on hydrogen?
You should be breathing dirt.
I think she's thinking of liquid hydrogen.
I don't know. I know that, like the Hindenburg, they used to have, like, their blimps were filled with hydrogen instead of helium, and that's flammable, and it was not a good idea. Yeah. I don't know who came up with that idea. But, so here's a pie chart of the universe. Hydrogen, dun, 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 followed by helium. And actually kind of this 3-to-1 ratio of hydrogen and helium, that actually supports the Big Bang. Who watches Big Bang? that relative abundance in the universe says, yeah, they're kind of on track with that whole thing, the Big Bang Theory. Okay, so this is the Earth's crust. Most of it's oxygen. And it's kind of neat. If you follow, the Earth did not have, how do I say this? It wasn't in the form of regular oxygen we're breathing. The thing that gave us the oxygen in our air was actually plants. You may know that. But like the early life was not humans, the early life was plant life. And they sucked in carbon dioxide and spit back oxygen, which reacted with the stuff in the Earth's crust and was kind of trapped there. This one creeps me out. Actually, I have gotten a YouTube video out there where it's a nursing student who, basically presents to the class, if we were to liquefy you, what would your body be like? Isn't that disgusting?
It's unfortunate.
I know. So you can see that 65% of you would be oxygen atoms. This is basically break you down into pile of atoms. So, icky. All right. So how many, I'm gonna ask it in this order. I'm gonna ask it gas, liquid, or solid. And just looking at a periodic table, kind of seeing that, I know you're not, you've heard of, you've heard a lot of those, calcium, iron, potassium. Let's see, you think most of those, how many people think most of those are gases? How many people think most of those are liquids? How many people think most of those are solids? You would be right. They're solids if you think about it, though, at a certain temperature and actually pressure of Earth. You switch planets, and they might be liquids or gases. That's kind of Yep, so under normal temperatures on Earth, these are gases. There's only a handful. 2 liquids. You're like, dude, really? Yeah. We're going to talk about it again later, but you remember the diatomic elements, the Hoffer-nickel? I told you, okay. Yeah.
There's the burr.
There's the burr, exactly. So a few of these elements have little subscript 2s, and that's because they're diatomic elements. And then the rest are solids. But we'd be talking about different kind of ways of chunking up different elements. And you can already start to get a sense. We're going to talk about chunking up elements as elements are metals, as the elements are non-metals. And this metalloids, there aren't very many. They're kind of metalloids or between metals and non-metals. They're kind of. Okay. So the 7 elements. So for this exam, and actually kind of for the rest of the course, you might want to know the ones where you have little subscript 2, the elements that are buddied up. So I'll kind of remind you, the mnemonic device is as kind of like a German-sounding last name, Hof, Ber, Nickel. And so Hoffer-nickel, I know it's kind of might be a stretch. So I'll put little subscripts 2 next to for hydrogen, for oxygen, a 2 under the F for fluorine, a 2 under the Br for bromine, a 2 under the N for nitrogen, a 2 under the I for iodine, and a 2 under the Cl for chlorine. So Hoffer-nickel. So when we get going and writing chemical reactions with these elements, or if these are the ingredients, or if these are going to be formed from our chemical reaction, you're always going to see them written with a little subscript 2. So here they are. These actually are in order of increasing weight. So we have the lightest to the heaviest up there. So, and here they are on the periodic table. We like 3 slides to talk about the 7 diatomic elements. Oh, well, what the heck. And the reason they're buddied up actually has to do with how their electrons, one looks at the other one's electrons and like, hey, why not? So that works well for them. Okay, so I have a periodic table to give you. Remember when I went around the room for 6 of you or whatever, and you guys told me the symbol for the name, or yeah. These are the ones you need to know for the test. So this periodic table, at the top of it, if you want to write test, you can, because this is what's going. You can't bring it to a test, but this is what it's going to be like on the test. So I'm going to give you one of these next time with your Unit 2 exam. And what some students like to do is to find, for instance, those are the number of protons. What are protons? 24 protons. What has 24 protons? What do you think? Chromium. Yes, chromium has 24 protons. Exactly. Chromium's an example of, if I give you the name chromium, you need to give me capital C, lowercase r. Okay? So, any questions? Okay, what element, use your periodic table, has 86 protons? Yeah, I would have to look it up. Is it radon? Yeah. Radon, very good. Know that one. Okay? So that's why sometimes students like to take the periodic table and kind of mark it up with your little markers. There might be other things you want to mark on there too coming up. Okay. So I don't know if this looks like a calendar or not. I've taught this for several years, but it's only been like the last year or so that I'm like, dude, this is so much like a calendar. Like, really? I'm like, yeah. Because here's the deal. You know how our calendar has Sundays, Mondays, Tuesdays, etc.? Okay? This is like that. Okay? It's got more days of the month, okay, or days of the week than 7. But this thing about columns or groups, okay, do all Mondays kind of have a similar feel to them? All Tuesdays? All Fridays? Okay. Okay, and that's the same way with elements in the periodic table. Mendeleev, I can't think of, Dmitri is his first name. Mendeleev, his birthday came and went recently, but he's the dude that actually took these in a dream, I guess. Many of these elements were known, and so he kind of arranged them, came up with this modern day periodic table. And basically what we see is that sodium, for instance, if you look at this first column, lithium, sodium, potassium, rubidium, cesium, and francium, they kind of have similar characteristics. Okay, we'll be talking more about that. Okay, so that's a group or a column. Sometimes, and it's coming up in your notes, we're going to call that a family. My daughter used to be listening to this song called "It Is Your Family." Okay, I can't remember what it was, but I liked it. Okay, up, down. So if I ask you on the test to kind of prick out something that would be kind of in the same family as sodium, you could go with potassium or lithium or rubidium. You would just go like this. Okay. So kind of what Mendeleev did in making kind of the whole Mondays line up with the Tuesdays line up, okay, that's actually called the law of periodicity. Think of it as kind of wrapping back around. Okay, we just finished Sunday, okay, and we're wrapping back around to a Monday. Okay, and that's what Mendeleev came up with. And I say it's wrapping around because if you go look at the number of protons, they keep getting bigger, they keep getting more and more protons in the center of the atoms as you go across and down. Okay? So that's called the law of chemical periodicity. So here's a periodic table from your textbook-ish, I think. So what's the number in each box? Protons, that's right. Yep, exactly. Do you have to memorize the names and symbols for all those? Can you see some color codings? I hesitate to say that because you might have the whole colorblind thing going out there, and that would work. We could still work with that. But I think you kind of maybe see some 3 colors there. Okay. So if a periodic table is worth its salt, actually when I first came I had this big old yellow periodic table. I can't remember how old it was, maybe 84. And the periodic table did not have the stair steps. I was like, what? Because the stair steps, I sometimes call it the jag. To me it looks like a jag instead of stair steps necessarily. But it's so important in chopping up, in one important way anyway, the periodic table. So it chops up the periodic table. It makes kind of a small triangular portion over there to the right, kind of an upside down triangle. Those actually are nonmetals. Over here to the left and down over here, these are metals. How many people think there's more metals than nonmetals? 1, 2, more solids, more metals, exactly.
And the weird stuff in the middle are metalloids.
Ah, the stuff that are kind of on the stair steps are like metalloids, exactly. Sometimes when we get going and later on, it's going to be important for you to be able to just say off the bat, is iron a metal or a non-metal? You would probably say it's a metal. Seems like a metal. Some are harder though. Oxygen, is it a metal or a non-metal? I like what you're doing. Look at the periodic table. That's what I do. Find oxygen. It's kind of hiding behind. It's actually
Behind the
it's a 6A. Yeah. Oxygen's a non-metal. So I want you to kind of be thinking about that. You'll always have a periodic table handy. You never have too many periodic tables. Okay, so look for the jag, and oxygen is a non-metal, exactly. And it has consequences. Yep, like Cameron said, the things along the stair step are metalloids, sometimes called semi-metals. And I've heard it described to me that what is a metalloid? Okay, it kind of depends on which chemist you ask, and maybe even on what day you ask him or her. Okay, it's a little bit iffy. Okay, you know. All right, so I already said this, up and down. Okay, these groups are called families too. The top underneath groups, you can put families. Okay. Now, periodic table, we're going with kind of the older convention. There's a new convention. But do you guys see the A's and the B's up here at the tops? Okay. The thing at the designation at the top is the group's designation. Okay. It's like the day of the week sort of thing. Okay. So one of the things is I want to emphasize these are A's. And do you see the A's over here? Okay. And these are B's. And these guys are also B's. We'll talk about where they fit in. Okay, so A, B, B. Okay. So not only the stair steps, but they're here to separate non-metals from metals, but there's other ways to look at the periodic table and to know some things, or to be able to talk intelligibly to somebody else about the elements. There are the main group elements, and on my slide, what I wish I would have said, and they're highlighted here, what do they all have in common? What did I just say on the previous slide? They are all A's, exactly. These are all A's, perfect. So in other words, the main group elements are group A elements. Sometimes you'll hear me group A elements, same thing. This is where, we have all sorts of things where it can be classified depending upon what sort of characteristic it can fall under, separate out different. My point was gonna be, the jag, all right, the stair step. Can you see that actually some of these main group elements are metals and some are non-metals? But they're all group A elements, they're all main group elements, the same thing. But don't be thrown off. So for instance, find oxygen, and it's a group A element, but which number is it? 6A. It is 6A, exactly. So 6A goes with oxygen, sulfur, selenium, tellurium, and chlorine. Okay, so the transition elements, what do they have in common? They're B's, exactly. Okay, so I told you these were B's, so these are transition elements. Are the transition elements, are they metals or non-metals?
Metals.
They are metals, exactly. Sometimes I've heard them called, and I think I may have slipped and call them this, in addition to calling them the transition elements, we could also call them the transition metals, same things. Sometimes I've heard these guys, and we'll talk again how these guys, the 58 through 71 protons and the 90 through 103 protons, we'll talk about how they fit in here in a minute. But sometimes these are called the inner transition metals. And I can't remember if I had a slide on that. Inner transition metals or elements, same thing. All right. Just chunking up the periodic table as we go. Okay. So we've talked about this is important, okay? The groups or the families. This is your family. Now, the periods would be like the weeks of the month, basically. So a period goes across. And so I'm emphasizing periods here. Okay? Now, each of the period has a single number. Let's see if you guys can find that number. On the periodic table, I just gave you, it's pretty clear. Okay? So the period numbers are over here. And they can be very important too. The period numbers on the board match up with these period numbers. This slide just doesn't tend to have them. So what period is oxygen in? It is in period 2. Does everybody see that? Very good. All right. All right. Well, let's talk about these guys down here. Let's pick on the lanthanide series. So if this is, what has 57 protons? This one right here, exactly. But you see how this skips from 57 to 72? Well, this goes from 58 to 71. See how that works? It's kind of inserted there. Okay, so the lanthanide series would be kind of thought of as being inserted right there. The reason they are kind of like two down by themselves, and some of you are familiar with the electrons. Where's my bead? Okay, the electrons actually, they are not all just random. The electrons are great about kind of being organized, and as it turns out, these are, if you're familiar with F electron, these actually start beginning at F. So these are these inner transition elements. We have the lanthanide series and the actinide series. Okay. And so, not so surprising, notice how the lanthanide is in period 6 and the actinide is in period 7. Okay, again, it kind of goes along with these numbers we see along the side here. All right, I did have one. So collectively, the lanthanide series and the actinide series are called the inner transition elements, or inner transition metals. And they are B group, though. They are definitely B group. Okay. Well, there are, I guess especially the A group, the main group elements, there are certain groups that you need to know by name. The first two fall into that category. So 1A, know that they are alkali metals, okay? I think I might have a picture of, here's a couple of alkali metals, lithium and sodium. And then going over one column, so that would be like Tuesday, okay? The 2A elements, these will all be metals, wouldn't they? The 2A elements are alkaline earth metals. To me, alkali metals and alkaline earth metals sound so similar. So what I do is usually know that the alkaline earth metals has more words to it. And then I make that 2A instead of 1A. So alkali metals, 1A, alkaline earth metals, 2A. Okay, so there is, I don't know if this looks familiar. A. Calcium, cute little calcium carbonate. And the other one's magnesium. You guys will be burning magnesium, probably this unit.
Cool.
And then we skip a bunch and go clear over to, now again, these are just special groups or families that you need to know the names of. And 7A, you may have already heard of the word halogen. 7A are the halogens. Halogen is a great gas that works well in light bulbs. Okay? So, there's our halogens.
What was the group 2A elements?
Alkaline earth metals. Mhm. Alkaline. And the other was alkali. So chlorine is Cl2, right? Hopper nickel, chlorine. It's a gas. Iodine is also, iodine is a solid. But one of the things about iodine is this beautiful purple, and it's great at going straight from a solid to a gas. I might have shown you that with the cold finger. Okay, so that's kind of what we see, that purple I2 going from a solid to a gas, and then actually solidifying back up here. That's I2. So the last one to know the name for is group 8A. And again, I'm kind of going with a little bit the older convention, with the A's and the B's and all that. So group 8A has 3 names, and you'll hear me use all 3 of them. Group 8A are noble gases, rare gases, and inert gases. If we kind of start backwards, the reason they're inert is, well, if you buy medicine, they talk about the active ingredient and the inert ingredient, okay? The inert ingredient is kind of there for the ride. The thing about these elements is if you have them, they don't like to play with anything else. They're just like, hey, I'm fine. The thing about them being rare gases actually kind of goes back to being noble gases. Rare gases means they're not very abundant in general. And the noble gas term, I think, came from nobility. Only nobility would. So. All right. So helium and neon. So just kind of some random picks of some elements. How many of them are liquids? 2. Mercury and chromium. Random picks. I think I have a slide coming up. Yeah. Okay, so, oops, sorry. So we've been talking about, and you guys answered some questions on your test about physical and chemical properties. These, an example of a bunch of physical properties, are listed here. Physical meaning you don't have to do any sort of chemical reaction to measure them. Okay? There's all different types of conductivity. It's interesting. There's thermal conductivity, there's electrical conductivity, there's probably sound conductivity, right? But with regard to thermal, or heat or electricity, in general, metals conduct those things, electricity and heat. In terms of them being shiny or lustrous, yes. In terms of them being, these kind of go together. Malleable means you can beat them into shape, yeah. Ductile means you can pull them into a wire, okay. So metals tend to kind of be conductive, lustrous, malleable, and ductile metals in general. And nonmetals are brittle and dull in their elemental form. So just kind of a glance at a periodic table. This one's cooler in the sense, and you won't have one like this, it has the names too, right? But notice that each box has two numbers. It has that whole number, which is what? The number of protons, exactly. And can you kind of see how it goes from left to right? They finish a period, they start a new period with the next number, okay? That's pretty cool. So we're talking more about what's in the box. So these will be due on Wednesday. And can I borrow somebody's book right quick? Make sure we're all okay. Thanks, Trish. I did not look at these, but I bet they're just fine.